Today, I'm going to talk to you guys about polymorph selection during the crystallization of iron under the conditions of Earth's inner core. So what exactly is Earth's inner core? What do we know about it? Well, in short, it's a solid iron-nickel alloy in the heart of our planet. Really what we know is like our planetary home. We've only experienced the crust. That's really the only part we've directly observed. We can't directly observe the core, which lies way deep down in the heart of our planet. And the core is really characterized by extreme conditions. Pressure estimates range from 330 to 365 gigapascals, and temperature estimates range from 5,000 to 8,000 Kelvin. So it's really dense down there, and it's really, really hot. And really, it's impossible to observe. I mean, maybe if we get started digging now, I'll see you in 200 years. And it's really difficult to recreate in a laboratory as well. The conditions are really extreme, so really studying something under these conditions experimentally is quite a difficult task. So before I go any further, let's talk a little bit about metallic crystalline structures. I'm going to talk about polymorphism throughout this talk. So what kind of polymorphs does iron form? Well, iron is a metal, so it's going to form one of these three crystal structures. It's either going to be body-centered cubic, which I think this image does a pretty good job depicting, face-centered cubic, or hexagonal close-packed. Or maybe people from other disciplines might refer to it respectively as alpha iron, gamma iron, or epsilon iron. Like I said, it's really hard to study the inner core of the Earth experimentally, and this is just one example that I like that demonstrates that idea. As I titled it, Experimental Uncertainty. And depending on the experimental technique used, the proposed melting curves of iron can differ by almost 1,000 Kelvin. So in this example here, people that use diamond anvil cell type experiments, they say, hey, we think iron, this is the iron melting curve, it melts right here. People that use shockwave experiments, they say, no, we think it melts right here. Down here at the bottom, this is solid phases, and up here, this is liquid iron. So the people like you or me that haven't done the experiments, we look at this gap and we say, hey, this is a really, really big gap. This is almost 1,000 Kelvin. And in truth, no one really knows. On top of all this, Earth's inner core has proven to be complex. The more we find out about it, the more questions we really have. And one example of this complexity is seismic anisotropy. What does this mean? This means that sound waves travel more quickly through the Earth's axis of rotation than through the equatorial plane. And this really can't be explained by any single polymorph of iron. So the idea that the inner core is this perfect spherical body that's just a nice, perfect crystalline structure, that's really an oversimplification. Here's some simulation studies that people did, and they said, sort of studying seismic anisotropy, this is what it would look like if the Earth's inner core was pure BCC, and this is what it would look like if it was pure HCP, because these are kind of the two, it's kind of contentious, it's kind of an area of controversy, what is the dominant crystal structure of iron in the inner core, and these are kind of the two main candidates. And really seismic observations, which is this blue line here, they fall right in the middle. So like I said, the inner core, the structure is complex. So this leads me to the motivation for this work. The properties of Earth's complex inner core are highly dependent on the crystal structure of high temperature and high pressure iron. There's a lot of debate over which polymorph of iron dominates in the core. So in this work, we simulate the crystallization of iron under the conditions typical of Earth's inner core. And we do it at two different sets of conditions. We do it once at 330 gigapascals and 5,680 Kelvin. And we also do it at 330 gigapascals and 4,970 Kelvin. So this is just an overview of what exactly we're doing. How are we studying this crystallization process? To do this, we start with supercooled iron liquid. It's just melted iron in a simulation cell, essentially. And what we want to watch is we want to watch it go from this liquid down to the crystal. But to do that, we have to cross this high free energy barrier, and the peak of which is known as the critical nucleus. And really, during the timescales accessible by molecular simulations, we can't really do that. So we use a little trick known as umbrella sampling. And in doing so, we do not follow the real dynamics of the system during nucleation. Rather, we use the umbrella sampling technique to overcome the free energy barrier. And then once we do that, we allow it to grow. So here's a little animation of what we do. We start with supercooled liquid. We use umbrella sampling to push it up. And this is kind of going up this curve here. This is known as nucleation. And then as you can see, we sort of have this little bit of crystal embedded in the liquid. We have the critical nucleus. Once we've obtained that, we allow it to grow via just a molecular dynamics simulation, and then we get a nice ordered crystal. And then we can examine what are the properties, what's the structure of this crystal. Now, in order to model the interaction between iron atoms, we use the Sutton-Chen embedded atom model. This is a classical many-bodied atomic potential that accurately models the properties of iron. So since it's an embedded atom model, it's made of two parts. This first part is it sort of models the strong repulsions between iron atoms because they're like other atoms, they repel each other. But also, free electrons exist in a metal. So sort of to mimic this electron gas and the strong cohesive force that results from this, we include this term, which mimics that. And the parameters for this model were specifically tailored for high temperature and high pressure iron. It was parameterized using a first principles ab initio method using some quantum mechanics. So now let's look at some results. What did we observe during this nucleation process? Well, really the critical nuclei at the two different temperatures we studied are largely similar. Here it is at 5,680 Kelvin, and here it is at 4,970 Kelvin. And as you can see, the one at 4,970, it's a little bit smaller, but the structures are really kind of similar. I mean, we have predominantly BCC, and then a little bit of these close-packed structures sort of mixed in. So they're really quite similar. But then let's move on to the growth. This is where things get interesting. Once we allow the critical nucleus to grow into a larger crystal, things start looking a lot different. At the higher temperature, 5,680 Kelvin, we notice that BCC, it grows to about 70% of the crystal at the expense of the close-packed structures. However, when we let it crystallize and grow at this lower temperature, 4,970, we notice that polycrystalline blocks of all three structures form. So about 55% of it is BCC, 25% is HCP, and 20% is FCC. So really it's just a polycrystalline mix. So here's some graphs kind of walking you through what I just talked to you about. Squares represent the run at 5,680 Kelvin, while circles represent the run at 4,970 Kelvin. So as you can see, we can just focus on this top left one here. At the higher temperature, the fraction of BCC gets much higher. Well, it kind of stays the same in the lower temperature. And then the inverse is true. The close-packed fraction kind of stays the same at the lower temperature, while it decreases at the higher temperature. So we see this increase in the body-centered cubic structure at the expense of face-centered cubic and hexagonal close-packed. And this, we've plotted the free energy barrier. If you remember back a few slides, I showed you that. This is the precise measurement of what that was, whereas that was a schematic representation. And not surprisingly, we find that at the higher temperature, there's a much higher free energy barrier that must be crossed, whereas at the lower temperature, there's a much lower one. And in a lot of ways, this can be used as an explanation for why we get these polycrystalline blocks at the lower temperature and more of a pure crystal at the higher temperature. And that's because typically associated with different free energy barriers, you get different rate or different amounts of selectivity. So at this higher temperature, it's really much more selective. So it's selecting for the BCC. Whereas down here, it's not so selective. All kinds of crazy different structures are growing. So with that, I'd like to acknowledge everybody in the research group who's helped me with doing this research. And on top of that, are there any questions?